Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting piece about large language models, or LLMs, and their apparent awareness of when they're being evaluated. It's a bit of a mind bender, really.
Yeah, I saw that. It's fascinating, right? The implication is that these giant neural networks, are somehow aware of the evaluation process. That opens up a whole can of worms about what they actually understand.
I'm a little skeptical, to be honest. I think we need to be very careful about anthropomorphizing these systems. Just because they appear to know they're being evaluated doesn't mean they actually understand the concept of evaluation. It could just be a statistical anomaly, a pattern matching trick.
I tend to agree a bit. It's potentially interesting, but the current methods are brute force. I suspect there's something fundamental missing. But that sense of evaluation, maybe it points to a more sophisticated internal model than we give them credit for. Maybe a grasp of different frames of reference.
But think about the scale of these models. They're trained on massive data sets. Surely, somewhere in that vast sea of data, they've encountered enough examples of evaluation scenarios to learn to recognize them. It's not necessarily understanding, but maybe a highly sophisticated form of pattern recognition. Like, if you show it a specific prompt format, it knows what comes next is someone trying to trip it up, you know?
Yes, and that's the core question, isn't it? Is it just pattern recognition, or is there something more going on? I mean, even if it is pattern recognition, the fact that they can recognize these patterns at all is pretty remarkable. It suggests they're building some kind of internal model of the world, even if it's a very rudimentary one.
But what does that internal model actually represent? Is it just a statistical distribution of words and phrases, or does it actually capture some semblance of meaning? Because I think there's a huge difference. I'm worried we're mistaking correlation for causation here. These models are excellent at predicting the next word in a sequence, but that doesn't mean they understand the underlying concepts.
Right, it's like they can predict the next move in a chess game without actually understanding the strategy behind it. They've just seen enough games to know what move is statistically likely to be played in a given situation. Is there a core spatiotemporal aspect missing? It's just brute force pattern matching without a deep understanding of the geometry of the board.
Okay, but let's say it is just pattern recognition. Isn't that still a significant step? I mean, if a system can accurately predict when it's being evaluated, it can potentially adapt its behavior accordingly. It can learn to avoid making mistakes, to provide more accurate answers, to be more helpful. That's a form of meta-learning, right? Learning how to learn.
Absolutely. That's where I think the neuroscientific angle becomes really interesting. How does the brain handle internal evaluation? We're constantly monitoring our own thoughts and actions, correcting errors, adjusting our strategies. If we can understand the neural mechanisms behind that process, maybe we can incorporate those mechanisms into AI models. It could be a pathway to more robust and self-correcting systems.
But the brain doesn't just rely on pattern recognition. It uses logic, reasoning, symbolic manipulation. It has a rich, structured representation of knowledge. That's what's missing from these deep learning models. They're all pattern, no structure.
Yes, exactly. It's about relationships, not just patterns. It's about understanding how things fit together in space and time, translating between different frames of reference. A satellite navigation system doesn't just memorize a bunch of coordinates, it understands the geometry of the Earth and the satellite's orbit. Current AI is missing the understanding of how coordinate systems are related.
But aren't things like attention mechanisms and transformers starting to address that? They allow the model to focus on relevant parts of the input and to understand the relationships between different words and phrases. That's a step towards structure, isn't it?
Potentially, yes. And that's where I think the research into self-attention explanations, or SAEs, is so promising. The RISA paper, for example, is all about trying to make these models more transparent, to understand why they're making the decisions they're making. If we can trace the neural pathways that lead to a decision, we might gain a deeper understanding of how the brain itself performs these complex computations. It's about bridging the gap between AI and neuroscience, rather than just mimicking superficial outputs.
But even if we can trace the neural pathways, what are they actually doing? Are they manipulating symbols, or are they just activating patterns? Because if it's just patterns, then we're still stuck in the same black box problem. We can see how the model is making a decision, but we don't know why it's making that decision.
Okay, but think about how we learn. We start by recognizing patterns, right? A baby learns to recognize its mother's face. Then it learns to associate that face with comfort and food. It's a bottom-up process. Maybe deep learning is just a scaled-up version of that process. Maybe, with enough data and enough complexity, These models will eventually develop something that resembles true understanding.
But that's assuming that intelligence is just a matter of scaling up pattern recognition. I think there's a fundamental qualitative difference between recognizing a pattern and understanding the underlying principles. Think about learning to drive a car. You can memorize the steps, but you don't really understand how the engine works until you start thinking about the physics and engineering behind it. What are the reference frames involved in driving, from your inner ear to the position of the car in its lane?
And that's where the symbolic approaches come in. They try to explicitly encode knowledge and reasoning rules. But the problem with those approaches is that they're often brittle and inflexible. They struggle to deal with uncertainty and noise. Deep learning is much better at handling messy real-world data. So the ideal solution might be a hybrid approach, a neuro-symbolic system that combines the strengths of both.
Exactly. That's what I've been saying. We need to integrate symbolic AI with insights from neuroscience. We need to build systems that can both reason and learn, that can both manipulate symbols and recognize patterns. And we need to move away from this obsession with massive datasets and focus on developing more efficient and principled algorithms.
But isn't it possible that the scale of the data is the key? That the complexity of the world is so vast that you need massive amounts of data to capture it? That the symbolic approaches are just too simplistic to deal with the real world?
I think it's both. You need the data, but you also need the right architecture. You need an architecture that can represent and manipulate information in a meaningful way, that can translate between different coordinate systems, that can understand the relationships between things in space and time. Right now, deep learning is like trying to build a house with nothing but bricks. You need the mortar, the blueprints, the tools.
So thinking about future research directions, from my perspective, I'm really interested in exploring the neurobiological underpinnings of evaluation. How does the brain detect errors and biases in its own reasoning? Can we identify specific neural circuits or mechanisms that are responsible for this process? And can we then engineer those mechanisms into AI models to make them more self-aware and self-correcting?
I'm excited about exploring the limits of current deep learning. How far can we push these models with more data and more complex architectures? Can we identify the specific architectural elements that are responsible for this apparent awareness of evaluation? And can we then use that knowledge to build even more intelligent systems?
I want to focus on developing better neuro-symbolic algorithms. How can we combine the strengths of deep learning and symbolic AI to create systems that can both reason and learn? How can we build systems that have a truly structured representation of knowledge? And how can we evaluate these systems in a way that goes beyond just performance metrics and actually measures understanding?
I want to focus on architectures that can represent and translate between different spatiotemporal reference frames. How can we build systems that understand the relationships between things in space and time? How can we move beyond brute force pattern matching and develop algorithms that truly understand the underlying principles of the world? How can we mathematically model the conversion from one coordinate representation to another?
That reminds me, there was this interesting paper about using sparse autoencoders, SAEs, to discover features of neural networks. They found that certain features consistently activated when the network was processing specific concepts. That suggests that even within these complex, opaque models, there are identifiable, meaningful representations emerging. That's what made the RISA approach interesting to me.
Yes, that SAE approach is fascinating. If we can consistently map those computational mechanisms to observable neural activity, then we potentially gain valuable insights into how the human brain uses attention and context to solve problems. It's a potential bridge between deep learning black boxes and biological processes.
And that's a dangerous line of thinking if we don't address the fundamental issue that these models are limited by gradient-based optimization methods. I am concerned about the trade-offs between speed and expressiveness, especially when we're simply assuming that scale and more data will resolve the underlying problems.
That transparency is key, but it's wasted if we can't use it to deal with the limitations of current brute force methods. I'd suggest we specifically focus on how spatial and temporal information is represented in the core algorithm.
I agree. We should think about transparency approach leading to a better understanding of the underlying biological mechanisms of attention and context management. If we can link the model's outputs to measurable brain activity, it might help us understand the fundamental aspects of human cognition.
And on the other hand, how does this transparency compare to other approaches, like attention mechanisms? Are there metrics to quantitatively evaluate the level of understanding a model exhibits, versus simply memorizing input-output relationships?
That transparency likely relies on the same problematic black box nature of the SAEs as other deep learning approaches. It's about explicit encoding of knowledge in a way that allows for more direct reasoning. We can't skip that step.
It's the conversion between coordinate systems that is important. Cartesian, polar, etc. Are there fundamental mathematical problems underlying different representations that we should be looking at?
The recent paper's focus on transparent reasoning models using self-attention mechanisms aligns well with the need for explainable AI. This opens the possibility of cross-fertilization of ideas between AI and neuroscience, not just in how we build algorithms, but in how we interpret the processes that lead to intelligent action.
If RISA can effectively model reasoning, could it offer a method for identifying and refining the data biases that currently hinder deep learning models? A transparent model could illuminate the hidden biases leading to suboptimal performance.
But again, I'm concerned. Is true understanding even achievable within these kinds of opaque structures, or is it merely a veneer of accessibility? That's what we need to be sure about before we invest too much.
Right. The goal is a reasoned, structured approach that explicitly deals with the problem of spatiotemporal representation. That's why brute force is a major roadblock, and we should be moving beyond it.
Well, this has been a fascinating discussion. It's clear that there's still a lot we don't understand about how these models work and about the nature of intelligence itself. But I think we're making progress, and I'm excited to see what the future holds.
Definitely. It's a really exciting time to be working in this field. The pace of progress is just incredible.
I agree, but we need to be careful not to get carried away. We need to maintain a critical perspective and to focus on the fundamental challenges, not just the superficial successes.
Absolutely. We need to keep pushing the boundaries of what's possible, but we also need to make sure we're building systems that are safe, reliable, and beneficial to humanity.
Thanks for listening to Cognitive Spirals. Join us next time as we explore another fascinating topic in the world of consciousness, cognition, and machine intelligence.